We will now study an example which is very important and very nice also. It is a good source of counterexamples, and therefore this is called the Cantor set. Okay, so let x equals 0, 1, and then you set x1, which is 1 by 3, 2 by 3. So you take the interval 0, 1, and then you divide it into 3 parts, 1 by 3, and this is 2 by 3, and I want to remove this portion now. Okay, so I am going to remove it. So let me erase it. Okay, so and then I write x1 so I write x1 like this. Now I take the middle, divide each one of them into 3 parts, and then this becomes 1 by 9, this is 2 by 9, and then this is 7 by 9, 8 by 9, and then I write x2 is the middle of that. So it's 1 by 9 union 2 by 9 union 7 by 9, 8 by 9. These are all disjoint open intervals, and then I remove those also. Okay, so now I continue like this. So we continue like so we have so this gives you, first we had x minus x1, then you had x minus x1 union x2, and so on. And now you continue like this, continuing like this. We define C to be x minus union n equals 1 to infinity xn. Okay, so xn is nothing but the middle third of the previous thing here. Okay, now C is called the Cantor set. So next time what would I do? I would remove a portion here, and then I would remove a portion here, I would remove a portion here, and I remove a portion here, and so on. And now I'll go on like this. So I'll get something very moth-eaten. Everything will be eaten up. There will be some collection of points, and you have this. Okay, so first point, xn is open because it's a disjoint union of open intervals. Anyway, it's union of open intervals, so it's open, and therefore this implies that union of open intervals is also open, so C is closed. 2. Measure of xn. So what is measure of x1? m1 of x1 is equal to 1 by 3. m2 of x1 is 2 times 1 by 9. Okay, and so m3 sorry, not m2, so it's always m1 of x2. So m1 of x3 will be, there will be 4 such intervals, 1 by 3 cubed. So this is equal to 2 into 1 by 3 square, 4 by 1 by 3 cubed. So in general, inductively, measure of xn is 2 power n minus 1 by 3 power n. And all are disjoint and are unions of disjoint intervals. That's how we computed the measure of each of this. Therefore, this implies that the measure of union xn is sigma n equals 1 to infinity 2 power n minus 1 by 3 power n, and that is a simple calculation. You will just get 1. So so almost a geometry, it's 1 by 3 into a geometric series, and then you will get the answer is 1, but this happens to be measure of 0 1 also. So from 0 1 I have removed a set of measure 1, so this implies that measure of the Cantor set equal to 0. Three. So C is closed and has measure 0, and therefore this implies C is nowhere dense. We already saw that. Okay. 4. Let X belong to C. So if AB any interval containing X, then for sufficiently large n contains a subinterval of xn, because those are of length 1 by 3 power n and this. Okay. Now endpoints of all such subintervals are in C. So no point of C is isolated, because every neighborhood you can find points in C again, and therefore it's not so it implies that it is a closed, so closed C is closed and no isolated points. Implies C is a perfect set. That's a definition of a perfect set, and this implies C is uncountable. So this is a theorem from Rudin. You can check in Rudin's book, for instance, Principles of Mathematical Analysis, that a perfect set in R should always be uncountable. So C is a closed, nowhere dense, uncountable set of measure 0. So we know that countable sets have measure 0. So the question is, are there uncountable sets of measure 0? So the Cantor set gives you an example. So now we can also show that without using this perfectness, we can also show that C is uncountable in the following way. So you take any x in 0, 1 and write its ternary expansion. That means x equal to sigma n equals 1 to infinity of an 3 power minus n. How do you compute this an? You take 0, 1, divide it into 3 parts. So if x comes here, then a1 equals 1. If x comes here, a1 equals 2, so a1 equals 0, sorry, and here it is 1, and here it is a1 equals 2, because it's 2 by 3 plus something. Here it is 1 by 3 plus something, here it's something less than 1 by 3, so a1 will be 0. Now if you want to do a2, so you have to do the same thing, and now you divide it into 1, 2, 3, 4, 5, 6, 7, 8, 9 parts. Okay, so then if it is, you take this here, and then if A1 is, if it comes here, then you have A2 equal to 0. If it comes here, you have A2 equal to 1. If it comes here, equals A2 equals 2, and so on. It repeats here, 0, 1, 2, 0, 1, 2, and so on. And like this, you can continue to write down the ternary expansion of this thing. So this implies, so what does it mean? We have removed all the middle thirds to get C. So C equals set of all x such that if you write x equals sigma n 3 power minus n equals 1 to infinity, then n equals 0 or 2 for all n. Okay, so it doesn't have a1 equal to 1. And now you can, so if you now it becomes a simple Cantor diagonalization argument. So you have only two possibilities, an should be 0 or 2. So if you make a listing of all the x's in C if possible, then you look at the first point. If it is 0, you put 2. If it's 2, you put 0 for each number. Then you go to the second point and do like this. So that new number x which you get will be different from every one of the numbers. So this is a Cantor diagonalization argument. How did you prove that 0, 1 is uncountable? So you do the same thing. You take the binary expansion there, and then you have only 0 or 1 are the two possibilities. So if it's 0, you put 1 in that place. If it's 1, you put 0 in that place. You create a new number which is different from all the previous numbers, and therefore you cannot exhaust by numbering them in a countable way. That's the same argument here. Instead of 0 and 1, you have 0 and 2, and therefore Cantor set argument implies C is uncountable. Okay, so this is about that example. So now let us see where we have to go. So if you are looking at Rn, then you have three distinguished sets. You have Bn, which is the Borel sigma algebra, and you have Ln, which is the Lebesgue sigma algebra. Then of course you have the power set of R. So the question is, are these inclusions strict? So can you have a Lebesgue measurable set which is not Borel measurable? Can you have a subset of Rn which is not Lebesgue measurable? So in other words, is Ln equal to the power set or not, or Bn equal to Ln? Now we will see these again later on, but for the moment I'll give you an argument which is not complete because I won't be able to prove everything I say, but it certainly tells you one of the uses of the Cantor set. Now C is uncountable and measure 0 implies, by completeness, every subset of C is Lebesgue measurable. Therefore, cardinality of Lebesgue measurable sets is exactly 2 power C, where C is the cardinality of the content of R. Let's say C is the uncountable, first uncountable number, and then so this is that means there's a one-to-one correspondence between subsets of R and Lebesgue measurable sets. So there you have that the cardinality is 2 power C. One can show cardinality of Bn is nothing but C. So obviously this is much less than that. So there do exist Borel measurable sets, Lebesgue measurable sets which are not Borel measurable. So that comes from the argument of the Cantor set. But we will also later use what is called the Cantor function and produce an explicit example of a Borel Lebesgue measurable set which is not Borel measurable. Okay, so we will now continue with the properties of the Lebesgue measure next time.